Even the researchers at Anthropic were surprised by what Claude just did. The AI system just cracked a mathematical problem that researchers thought would be beyond any language model, and it's forcing everyone in AI to rethink what's actually possible. This isn't a stunt. Anthropic just published research showing Claude can rigorously solve complex mathematical proofs that require the kind of step-by-step logical reasoning most people assumed AI systems simply couldn't do. We are talking about the Riemann Zeta function here, one of the most famous unsolved problems in pure mathematics. Now here's where it gets interesting. Claude didn't just throw an answer at it. The AI worked through the mathematics the way a human mathematician would, showing every step, catching its own errors and correcting them. That's not pattern matching, that's actual reasoning. For years, researchers have debated whether AI systems like Claude actually think or if they are just really impressive copying machines. This research doesn't settle that debate, but it pushes the goalposts so far that it changes the entire conversation. The implications are enormous. If an AI can reason through rigorous mathematical proof, what else can it actually do that we've been wrong about? And how many problems have we assumed were permanently beyond AI's reach? Let's zoom out for a second and talk about what the Riemann Zeta function actually is, because understanding why this is such a big deal means understanding why this breakthrough matters. The Riemann Zeta function is a mathematical function that sits at the intersection of pure mathematics and physics. It describes patterns in prime numbers, and prime numbers are the atoms of mathematics. Basically, the Riemann hypothesis is one of the $7 million Millennium Prize problems. If you solve it, you win $1 million. Mathematicians have been attacking this problem since 1859, and it's still unsolved. That's 167 years of the world's brightest minds throwing everything they've got at it, and nobody's cracked it yet. The reason it matters isn't abstract. Prime numbers are the foundation of internet encryption. Every time you send a secure message, check your bank balance online, or buy something on the internet, prime numbers are protecting your data. If someone cracked the Riemann hypothesis, they could potentially break modern encryption. So when Claude starts working on mathematical proofs related to the zeta function, we're not just talking about academic curiosity. We're talking about AI systems attempting to solve problems that have stumped the world's best mathematicians for more than a century and a half. And here's the thing that changes everything. Claude didn't just look up an answer. So how does Claude actually do this? The key lies in something called chain-of-thought reasoning. Instead of just generating an answer, Claude is trained to write out its thinking step by step. Imagine you're trying to solve a complex puzzle. You don't just blurt out the answer, you work through it aloud, checking your logic at each stage. Claude does the same thing, but with mathematics. The Anthropic research shows that when Claude encounters a mathematical problem, it breaks it down into smaller logical pieces. It identifies what it knows, what it's trying to prove, and what intermediate steps it needs to get there. Then it works through each step methodically. But here's where it gets really interesting. Claude catches itself making mistakes. When it realizes it's gone down a dead end or made a logical error, it backtracks, reconsiders, and tries a different approach. That's not something a simple statistical model does. That's something that looks a lot like actual mathematical thinking. The researchers tested Claude on multiple proof problems, not just one lucky success. The consistency across different mathematical domains suggests this isn't a fluke. Claude can apply rigorous logical thinking to problems it's never specifically trained on. This is what separates genuine reasoning from pattern matching, and it's the moment everything changes. The Anthropic research includes specific examples of Claude working through mathematical proofs. One case involves complex analysis. That's the branch of mathematics that deals with functions of complex numbers. In the examples Anthropic published, Claude worked through multi-step proofs, each one requiring it to know theorem names, understand their implications, and apply them correctly in sequence. But Claude didn't just work through textbook problems. It handled novel proof strategies that required genuine mathematical creativity. In one example, Claude identified an alternative proof path that was more elegant than the standard approach, something that suggests it wasn't just retrieving memorized solutions. The error correction is particularly striking. When Claude hit a logical dead end, it didn't double down or try to fake it. It explicitly acknowledged the error, traced back to where the mistake occurred, and started a new approach. That's the mathematical equivalent of professional debugging. The math problems ranged from intermediate difficulty proofs all the way up to genuinely advanced mathematics. We're not talking about high school algebra here. This is university-level pure mathematics that requires deep understanding of abstract concepts and their relationships. And here's what most coverage is missing. Claude succeeded even when the proofs required knowledge that wasn't obvious from the problem statement itself. That's reasoning, not retrieval. This brings up an obvious question: can other AI systems do this too? The short answer is not like Claude. Other large language models have tried to tackle mathematical reasoning, and they've had mixed results. GPT-4 can handle some mathematics, but usually simpler problems. Gemini has similar constraints. Most AI systems start breaking down once mathematics gets abstract enough. They can follow simple algebraic steps, but struggle when proofs require what mathematicians call abstract thinking, the ability to reason about concepts that don't have concrete real-world analogues. What's different about Claude is that Anthropic trained the system specifically for chain-of-thought reasoning. The model learns to articulate its thinking, not just produce outputs. That seemingly small difference has massive implications for how well it can handle complex logical problems. It's the difference between showing your work and just calling out answers. Traditional mathematicians who work through proofs by hand have always known that showing your work matters. You catch mistakes. You identify missing steps. You find alternative approaches. Anthropic took that human insight and built it into Claude's training from the ground up. The result is an AI system that reasons more like a mathematician than previous systems did. That's not because Claude is fundamentally different hardware-wise. It's because it was trained differently. And that suggests every AI lab should be rethinking their training approaches right now. What does this research actually mean for the future? First, it's a wake-up call about AI capabilities we've been underestimating. For years, the conventional wisdom was that large language models were good at language, but bad at logical reasoning and mathematics. This research punches a hole in that assumption. If Claude can handle rigorous mathematical proof, then we've been selling AI reasoning short across the board. Second, it matters for AI safety and alignment. Rigorous logical reasoning is something you want in a powerful AI system. If Claude can be trained to think through problems step by step instead of just pattern matching, that's something that could make AI systems more transparent and trustworthy. You can see how it arrived at a conclusion instead of just accepting a black box output. Third, it opens up entirely new applications for AI systems. Mathematics is used everywhere, from designing microchips to modeling climate systems to cryptography. If AI can handle rigorous mathematical reasoning, then mathematicians could partner with AI to tackle unsolved problems. We could see AI systems generating novel mathematical insights that help humans solve billion-dollar engineering problems. And fourth, this forces a philosophical conversation. If AI can truly reason through mathematical logic, what does that tell us about the nature of reasoning itself? So what happens next? Anthropic isn't just publishing this research for fun. They're actively building Claude to be better at mathematical reasoning and logical problem solving. The practical applications are already starting to show up. Researchers are using Claude to check their own proofs, to identify bugs in mathematical logic, and to explore new approaches to unsolved problems. One team recently used Claude to help verify a complex proof that took months to check manually. Claude did it in minutes. That's a time savings that compounds across every mathematics department and research lab in the world. But there's a bigger picture here. This is part of a pattern we are seeing across AI development right now. Each generation of AI systems is demonstrating capabilities in domains we thought were beyond AI's reach. We thought AI couldn't reason. Now it's doing mathematical proof. We thought AI couldn't code reliably. Now it's writing production software. The track record suggests that whatever we think is impossible for AI today is probably just something we haven't trained AI to do yet. That's both exciting and unsettling. It's exciting because it means we haven't found the ceiling on AI capabilities yet. It's unsettling because we are running out of domains where we can confidently say AI will never do this. The mathematical reasoning breakthrough shows that AI development is moving faster than most people realize. Here's what this all means for you and everyone watching. Claude's ability to work through mathematical reasoning doesn't just matter if you're a mathematician or an AI researcher. It matters because it shows us that AI systems are becoming more capable at logical reasoning than we thought possible. That's the kind of capability change that's about to reshape every field that relies on complex problem solving. The research Anthropic published isn't a finished story. It's an opening chapter. Claude's mathematical reasoning will get better as the system is refined and retrained. Other AI labs are definitely rushing to replicate these results with their own systems. Within a year, we are going to see AI-assisted mathematical research becoming standard in universities and labs. That means fewer mistakes, faster discoveries, and solutions to problems that have stumped researchers for decades. But it also means we need to stay vigilant about how AI systems are trained and deployed. The better AI gets at reasoning, the more important it is that we build these systems responsibly. Subscribe to this channel if you want to stay on top of breakthroughs like this one as they happen, because AI capabilities are shifting faster than the headlines are tracking them. Follow for daily AI news.